Here we go, good old Anne. A book is sitting on a level desk. Which of the following statements are true? A, there are no forces acting on the book because it's not accelerating. If it's not accelerating, does that mean there's no force? What does that mean? It means that when you add up all the forces, the total works out to exactly 0. In fact, I can now say when you add the forces vectorially, if there was slanty forces, if you add everything up tip to tail, they will all cancel out. As a triangle, you would end up back where you started from when you did your tip to tail adding. But yeah, so false. The magnitude of the normal force between the book and the desk equals the magnitude, oh, missing the N in there, I'll have to fix that, of the gravitational force on the book. I think that's true, Cart. Yeah, mg and Fn equal the same. The net force on the book is, oh, that's true, because it's not accelerating. D, friction is what's holding the book on the desk. I think as long as the desk is flat, it could be made of ice and the book will still stay there. Yes? So I think false. I like that. Number 2, find the this is a job for a free body diagram. So I have M1G, normal force number 1 to go with mass number 1, tension, M2G, normal force number 2 to go with mass number 2, tension this way, and F applied this way. Who's winning? F applied. Good morning, good morning.
Good morning.
Here, I'll pause for a second. That's okay. So continuing on, we have winner minus loser plus winner. Is M1G going to show up in this equation? No. It will if there's friction, which we'll do later on, equals M all A. Tension cancels, always nice. A is going to be F applied divided by the mass of all of them, which is M1 plus M2. It's going to be 24 over 8 plus 12. I can do that in my head. 24 over 20, divide by 4, divide by 4, 6 over 5. Is it 1.2? Meters per second squared. If you got that, 2 out of 2. Otherwise, I would probably go something like half mark for that, half mark for that, half mark for the numbers, half mark for the answer. Find the tension. I would probably use mass 1. You can get the same answer with mass 2, but the reason mass 1 is a bit nicer is it's going to be tension equals M1A, because that's what's pulling mass 1 forward, which means it's going to be 8 times 1.2, 9.6 newtons. I would give you 1 mark for the equation, half mark, half mark. Did anybody do mass? Did anybody use mass 2? Nope. You did? Oh, you did? So you would go 24 minus tension equals M2A. You would do the swappy dance. You would go tension equals M2A minus, 24 minus M2A, and you would still get 9.6. Yep. Number 3, same question as number 2, but with friction. So I'll add that to my free body diagram in a slightly different color. I'll do it in green. We would have friction force number 1 to go with mass number 1. And don't forget, I would also have friction force number 2 to go with mass number 2. Okay? And they want me to change this to what? 50? What did I say? 50 newtons. Because that's what the instructions clearly said. Yes, Sean? Yes. Okay. Who's winning? I think now it's going to be F applied. There's going to be minus tension minus friction force number 2 minus friction force number 1 plus tension. That equals M all A. And this card, I think you were the one I kept saying, this is why I would argue friction doesn't make it tougher as much as longer. I've got more stuff, but hey, tension still cancels, yay. And to get the A by itself, it's still going to be divide by M1 plus M2. The applied force is 50 minus mu times normal force number 2 minus mu times normal force number, I don't know normal force number 2. Oh, but look. Another force the same size as normal force number 2. What? M2G, yes? So I don't want to rewrite all this, so I'm just going to go cross that out and put a little M2G there, and M1G. And this is where M2 and M1 show up. They show up if we introduce friction, but since they're not along the rope, they won't show up otherwise. I don't think I would do this on a test, but for what it's worth, I could also add an extra force pushing down or lifting up, and that would just mean, McKenna, that your normal force wasn't mg. You'd have to, everything down equals everything up, somewhere off in the margin, and actually calculate the normal force. Would that make it tougher? Make it longer. That's all. So it's going to be 50 minus, what's mu? I don't know what's mu with you. 0.12, 12 times 9.8 minus 0.128 times 9.8 all over 12 plus 8. Running out of room here. I'll put my equals right here. Fraction, definitely brackets around the top. 50 minus 0.12 times 12 times 9.8 minus 0.12 times 8 times 9.8. Close off the top, divided by bracket 12 plus 8. I know 12 plus 8 is 20, and in my homework I typed 20, but I think I've told you, Adrian, on a test, on a test or a quiz, I do everything on my calculator. Yeah? Did you get 1.324? All right, 1.32, but I'll keep that 1.324 for further calculations. So far, so good. Tension. I looked at my free body diagram and I said, I think I'm going to use mass 1. Did you use mass 1, Josh, or did you also use mass 2 for tension? Okay, because I think here it's going to be, the tug of war is tension minus friction force number 1 equals M1A. Tension equals M1A plus friction force number 1, which is mu times normal force number 1. I don't know normal force number 1. Oh, but look. Tension equals M1A plus mu M1G. It's going to be M1 was 8, yes? 1.324 plus 0.12 times 8 times 9.8. Those are the right numbers? I'm going from memory. I think so. 8 times answer button plus 0.12 times 8 times 9.8. Did you get, oh, is it 20 even for tension? People nodding? I see people shaking their head. No, nodding? Yeah. Am I right? It's a fluke. Newtons. 2 marks. And again, half mark, half mark, half mark, half mark. Elevator questions. You know what elevator questions are a good job for? Yeah, and in Physics 11, I probably said to you, draw one for each question. I'm going to draw a generic one over here, Josh, because it seems to me the tug of war is between the obvious one and the normal force. The arrows could be bigger or smaller, Allie, but I'm telling you, that's the tug of war. And also, when I wrote normal force, I'm thinking bathroom scale, because that's what a scale measures. Which way are we accelerating up? So, which way are we accelerating? Up. Boy, said that wrong. Which way are we accelerating? Up. So it seems to me, Wes, that normal force is winning, mg is losing, equals ma. Wes, what's this question asking me to find? What's it really asking me to find, folks, when it says find the scale reading? Normal force, okay? Now, now that you've seen this, you saw this last year, I would have no problem this year adding one more step and saying, okay, what does the scale read in kilograms? How do I go from newtons back to kilograms? It's divided by 9.8. Or what if I told you the scale reading in kilograms and I needed it for newtons? How do I go from kilograms to newtons? Times by 9.8. It's hidden in that weight equals mg equation. Okay? So meanwhile, I'd get the normal force by itself. It's going to be m 60, a 1.2 plus 60 times 9.8. I could do that in my head. It's going to be 60 times 11. 660? Or am I wrong? Yeah, 660? Newtons. Ooh, this one I won't do in my head. Accelerates. Am I wrong? Oh, well. Get a good one for your phone, then, temporarily. Oh, you didn't have your calculator out yet? Oh. Disappointment abounds. And you were the last one to get here. Boy, I wish I was doing the water thought experiment today, because then you'd be getting wet, fireman, right? Oh, okay, sorry. Elevator accelerates downwards. So I think if we're accelerating downwards, gravity is the winner. Normal force is the loser. That equals ma. By the way, what we're really saying with that 660, if I did not divide by 9.8, even though this person's actual mass is 60 kilograms, they feel like they have a mass of 67 kilograms. You okay there, Noah? Yeah. Okay, that's all we care about. How would I get the Fn by itself here? Swappy dance. We'll get mg minus ma equals Fn. So it's going to be 60 times 9.8 minus 60 times 2.25. Do you get 453? If I'd said, what does the scale read in kilograms? On the way down, this person feels like they have a mass of 46.2 kilograms, even though their actual mass is 60. What if we accelerate down even faster? Would they feel heavier or would they feel lighter? And convince me. What do you think? If we accelerate down faster, more than 2.25, are they going to feel heavier or are they going to feel lighter? McKenna, what do you think? Lighter? Convince me. I agree with you. You're right. Okay. Ready? We're in physics 12 now, right? Don't you have an equation sitting right there? If that A gets bigger, what happens to this overall answer? When you subtract a bigger number from mg, what will your answer work out to be? Smaller. That would actually, like you were going to give me a lovely verbal, and that was okay. But honestly, now I would say, I would write that out and simply say, as A increases, normal force decreases. So now here's the next thought puzzle. What if A was bigger than 9.8 going down? What if we had rockets on the elevator and it was accelerating down, let's say, at 20 meters per second? What would happen? Ooh. Well, when you plug the numbers in here, you get a negative answer. You would get a negative, what the heck would a negative normal force be? Sorry? What would happen, I think, is you would fly off of the floor and you would go smack against the ceiling, and now you would feel the ceiling pushing down on you. In fact, if we did a really nice number, if we accelerated down at exactly 2 Gs, you would feel 1 G normally, but you would be standing upside down on the ceiling, but that would feel just fine, assuming the impact didn't injure you too much. You would be going, weird, huh? Now the ceiling is the floor. Does that make sense? It's kind of a little thought puzzle, okay? Okay. Anyways, C, elevator moves up at a constant velocity. If you're at a constant velocity, what's A? And so we can say it's a tie. The normal force equals mg. So it's going to be 60 times 9.8. It's going to be 600, take away, what, 12, Mr. Dewick? No, yeah. So 588, is that right? And I think I said this last year, but I'll repeat myself. I think I said this last year, but I'll repeat myself. See, I did that. There is no experiment that can detect constant velocity. Einstein said, if you're going at a constant velocity, or if you're at rest, you can't tell the difference, which means maybe there is no difference. It's all relative. Yeah. What's the answer for D if we're accelerating downwards in free fall? And this was Einstein's, he called this his happiest thought. When he was trying to work acceleration into special relativity, he said, hey, wait a minute, here's a system where I have gravity. Gravity's definitely acting, but if I look at it from the viewpoint of the person in the elevator, they feel no gravity. And so I've got two reference frames that I can jump from, one with gravity, one without, and that was kind of his starting point for the theory. The mathematics was much tougher. Anyways, I totally agree, 0. Can you give yourself a lovely score, please, out of 19? If you need to lawyer with me, now.